Wait, I can't see your screen.
Hold on a minute.
Oh wait, now I can. There we go.
What number am I writing?
7.
Okay. Huh. I
Alright.
didn't see it prior to that, though. Wonder what was going on there. But that's okay. We got it working now. Go ahead and verbalize the problems. I'll write them out, and then we'll try to solve them.
Okay, well the question is write an explicit rule for this arithmetic sequence based on the given terms for the sequence.
Okay. What's the sequence?
And it's A4 equals 11 and A7 equals 17.
Okay. Where you always want to start on these kind of problems is with the explicit general format, which is what? A to the nth term equals what? For an arithmetic. Yeah, A1.
And then minus n, I think. I have it written down.
It's plus the common difference times n minus 1.
Okay.
Okay. And let me just say something about this. This is one of those formulas you need to memorize, but let's say you forgot it. Okay? Well, let's write out an arithmetic sequence. There's 1, 2, 5, 8, 11. And let's see if the fourth term is indeed 11. So is this different than this? Hold on to that for just a second before we get to it. But mainly I want to give you a way of making sure that your memory remembers this thing correct.
Okay.
So if I wanted to know the fourth term, it would be the first term, 2, plus the common difference, 3, times n. Well, n is 4, so this would be 4 minus 1. Well, that gives me 11, which is indeed the fourth term. So I know I have it right.
Okay.
Okay? That's the most important thing, is come up with an arithmetic sequence where it's really easy to see what the fourth term or the third term is. Plug it into your formula and make sure you get the right answer. So this is definitely the right formula. Okay? Now, this is a particularly difficult problem because they don't give you the first term. They don't give you the arithmetic sequence. We don't even know what the common difference is. But they've given us a sub 4. So a sub 4 always is a sub 1 plus the common difference times 4 minus 1. And a sub 7, and all of that's incidentally equal to 11. And a sub 7 is a sub 1 plus the common difference times 7 minus 1. And that's equal to 17. Well, notice what I have here. I have 2 equations and 2 unknowns. In other words, this top equation is a sub 1 plus d times 3 equals 11. Bottom equation is a sub 7 plus d times 6 equals 17. Well, there's only 2 unknowns there.
So did you just get rid of the a sub 1?
Excuse me. That's a sub 1. Nothing like confusing the student. Notice what I have now is I could write it as 2 equations with 2 unknowns. In other words, a sub 1 plus 3d equals 11, and a sub 1 plus 6d equals 17. What's the best way to solve that system of equations?
Probably the way you just wrote it.
Subtraction.
Oh,
You can
okay.
always choose, whenever you have two equations and two unknowns and you're solving them by elimination, which is what we're going to
Well,
do.
how do you know to solve them by elimination?
I always use elimination when I'm looking at standard format. Standard format is where you have both variables on the left and you have a number on the right.
Okay.
You could use substitution, but it's not the best way to go, and you'll see why. I can choose elimination and I can subtract. Let's call this equation 1. Let's call that equation 2. I can subtract either 2 from 1 or 1 from 2. I'm always allowed to do that. Well, notice that the a sub 1 gets completely eliminated if I do either of those.
Mm-hmm.
If I merely subtract 2 from 1, I get minus 3d equals minus 6, so d equals 2. Once you solve for d, now you can go back up here and a sub 1 must be 5 if d is equal to 2. So we now have a sub 1 equals 5. The common difference equals 2. Therefore, the explicit is 5 plus 2 times n minus 1. And even that can be simplified a little bit, which you always want to do. That's 5 plus 2n minus 2, which becomes 2n plus 3. There's your answer.
How did you go from, oh, you distributed it.
Just
Okay.
distributed the 2, exactly.
Okay, and then how did you get 5? How did you know that ace1 is
Well,
5?
once I got d equals to 2, now I'm going to go back into this equation right here, plug in d of 2, and
Oh,
a sub 1 plus 6 equals 11, therefore a sub 1 becomes 5. In other
oh,
words,
okay.
I do it the same way you solve all systems of two equations and two unknowns when you're using elimination. Is you solve for one variable. After you've eliminated one variable, it's pretty easy to solve for the second. And once you've solved for that second variable, you go back into either equation, substitute the solution for that variable, and then you only have one equation and one unknown. And so you can always solve for both variables.
All right.
This is about as hard as these are going to get, where they merely give you this little amount of information. Normally, the problems, they give you the sequence, and they start asking, you know, what's the 23rd term of the sequence? Well, what is the 23rd term of this sequence? Now that we have our answer, over here on the lower left, we have the explicit definition. So what would the 23rd term of the sequence be?
So, do I still keep the like 5 plus 2?
N is always, no, I simplified that. In other words,
Oh,
this was the final answer right here.
okay.
Okay, so you can plug into that. And n is always n, whatever n is. In other words, n in this case is 23.
Okay.
So a sub 23 would be 2 times 23, 46 plus 3. That's the 23rd term in that sequence.
Okay.
And in fact, the common difference we figured was 2. So here's the sequence. 5, 7, 9. If I go out, the 23rd term is going to be 49.
All right.
All right. What else you got?
Okay.
Have you had geometric sequences yet? Or are you just in arithmetic?
I think we've just done arithmetic.
Okay.
There's another question, and it's a word problem.
Okay.
But it says, at a pizza shop, 2 small pizzas, a liter of soda, and a salad costs $14. one small pizza, a liter of soda, and 3 salads cost 15, and 3 small pizzas and a liter of soda costs 16.
All right.
What is the
Start again from the start because I was not quite with you. 2 pizzas, 1 liter of soda, and 1 salad cost how much?
$14.
What's the next one?
1 pizza, 1 liter of soda, and 3 salads cost 15. And then 3 pizzas, a liter of soda, and a liter of soda cost 16.
That it?
And it says, yep, what is the cost of 1 small pizza, of 1 liter of soda, or 1 salad?
Okay. What we have here, what's the first step I should do? All word problems, always you should do this as a first step. And it is truly the secret of word problems. Once you always do this as the first step, these will not give you any problems anymore. Define your variables.
So what does that mean?
Well, I could say X is the cost of a pizza. Well, that's what they want. You define your variables by going to the last sentence. The last sentence says, what is the price of a slice of pizza, right?
Mm-hmm.
Well, in order to figure out what pizza costs, I actually have to figure out what a slice of pizza costs, what a liter of soda costs, and what a salad costs. So,
Okay.
I can use different, I don't have to use X, Y, and Z. I could use P, soda would be S, salad would be S. So just for convenience sake, let's say X is the price of 1 slice pizza. And I've really found that being very, very specific on your variables helps a lot. Y is the price of 1 liter of soda. And the reason it makes sense to be specific is sometimes it's the number of slices of pizza and sometimes it's the price of a slice. So if you're not specific, you're going to have a hard time figuring out which it is. And this is...
Well, it's not asking us for slices. It's just one. It just asks what's the cost of a pizza.
Right. But in order to figure it out, we have to solve this system of equations. Okay. Here's my system of equations. What is it going to be? In other words, I've written it, except I've written it without the variables that we chose.
Oh, okay. Well, the first one would probably be 2x plus y plus z equals 14.
14, right?
And then the second one is x plus y plus 3z equals 15. And the third one is 3x plus y equals 16.
Okay. Now, we have 3 equations and 3 unknowns. It means we're going to be able to solve for each variable.
Okay.
It only wants us to solve for x, but we might necessarily have to solve for all 3.
Well, it asks for all 3 eventually.
Oh,
it says
does. Okay, good. I'm glad it does. Okay, how do we solve 3 equations and 3 variables?
well, we have to number our equations.
Good, I love that, yes.
Okay, so 1, 2, and 3.
What's the
And
strategy? What's the first thing we're going to do?
we're going to use elimination and eliminate one of the variables.
Okay, which variable can I eliminate pretty easily?
Probably y.
Yeah. In fact, my goal is to come up with an equation 4 that has a variable eliminated, and then come up with an equation 5 that has the same variable eliminated.
Okay.
Okay. Well, it's pretty easy to eliminate y, as all I have to do is subtract 2 from 1.
Mm-hmm.
So what's equation 4 going to be?
So, okay, that's just going to be, wait, what did we do to the first equation? Or what are we going to do to the first equation?
What we're doing is subtracting equation 2 from equation 1. Or we could do 2 minus 1. Either way gives us the same thing. It's just if we do 1 minus 2, we have negative signs. If we do 2 minus 1, it's a little cleaner. Not really. We still have a negative sign. Let's do 1 minus 2. What do you get when you subtract 1 minus 2?
So that'll just be, so it'll be x, and then there wouldn't be y, right?
Right. The y gets eliminated.
And then x minus 2z equals negative 1.
Right. Okay. Now, we have to eliminate the same variable using 2 different equations. We can't, in other words, to get equation 5, we can no longer use equations 1 and 2. But we can use 2 or 3, 2 and 3, or 1 and 3.
Okay.
Well, both of those, if we subtract, we eliminate y again. So pick 2 to use.
Well, the easiest. So, would I subtract 1 from 3 or 3 from 1? Or does it not matter?
Either way. You can, in other words, whenever you have 2 equations, you can always add those equations, you can always subtract them. That's the rules of algebra. Okay? Our goal is to eliminate y. Well, I'm going to eliminate y regardless of whether I do 3 minus 1 or 1 minus 3.
Okay, I'd probably do 3 minus 1.
Okay? What do you get?
X. Oh, wait.
It's okay. You got X. You can assume a 0 there.
Okay.
So you got 0z minus a positive z.
Okay, so it'd just be z.
Minus z.
Oh, minus.
Remember, I'm doing 3 minus 1. Okay. Now we got our goal accomplished. We have the equations 4 and 5, and they both are missing the same variable. This would not be any good if this was x and y and this was y and z. I wouldn't be able to go any further. But as long as I eliminate the same variable, now I just have a system of 2 equations and 2 variables. How do I solve that?
By just substitution.
Still elimination works best. Whenever you see both variables on the left side and nothing but numbers on the right side, elimination is almost always going to be the easiest way to go.
Okay.
In other words, the only time substitution is really very good is if one of the equations is fully defined for one of the variables. In other words, if equation number 5 was x equals 2 plus z, well, now I might do substitution because the second equation would be fully defined in terms of x. But that's not what we're looking at here. In fact, we're looking at something that's quite simple. I can subtract one from the other. What do you get? Subtract 4 minus 5.
4 minus 5. Okay, well, would the x's just cancel out?
Yep, as long as you're subtracting. If I was adding, they wouldn't. But if I'm subtracting, they will disappear in the same way that the y's disappeared when we did 1 and 2 and 1 and 3.
So say number 4 was the negative x. Would I add in that case?
Yes.
Okay.
Yes. You always want to do what's easiest. If this was a negative x, well, now I can add both equations instead of subtracting them, and that'd be the easiest thing to do. But since it isn't, the easiest thing is subtraction. Now, a lot of people will go out of their way to turn one of these, in other words, they maybe would multiply the top equation by -1, which you certainly could do. Notice what happens if I do that. I multiply equation 4 by -1. I put a negative there. I put a positive there. I put a positive there. Now I can add the two equations, and x will still go away, but the arithmetic's a little easier, isn't it?
Yeah.
It's not -2z minus a minus z. It's the x's. If I'm adding these two, then this becomes z equals 3. So it's okay to do that, to make one of the equations such that you can add equations instead of subtracting them. And in fact, I usually recommend that. If you have to manipulate an equation in order to get a variable to disappear, I usually suggest doing it in a way where you can add the two equations. Just because people don't make as many mistakes when they're adding as they do when they're subtracting. So if you can add them, you're generally better off. But if they come ready served on a platter like that, why not just subtract them? Why take that extra step? Well, if I do 4 minus 5, the x's disappear. Minus 2z minus a minus z gives you minus 1z. And minus 1 minus 2 gives you minus 3, which gives you z equals 3. Now, once you have one variable solved for, then you basically just have to go backwards. What's the next variable we can solve for?
Z.
I just solved.
We could solve for y.
Nope. It's hard to solve for y because we don't know what x is yet.
Oh, right.
In other words, you have to go back to either equation 4 or 5, which now that we know what z is, it's easy enough to solve for x. X must be 5. In other words, and always go into the simplest equation you can find, which is this one right here. It's a positive 2. I can substitute z of 3 and come up with the solution almost instantly. So
you can use that equation.
5. What's that?
So you don't have to use one of the original equations?
Well, now you do to solve for y. In other words, you solve for your first variable, then you go into one of the equations that only has two variables, which allows you to solve for the other variable, x. But now, if I want to solve for y, I got to go back into one of those three equations. Okay, well, that's easy enough to do. Which one would I pick?
Y. Oh, you mean which one to solve for?
For solving for y.
Okay.
This might be the easiest one to pick, notice. There is no z in that one.
Right.
I put it in there merely for demonstration purposes. But to solve for y, all I have to do is substitute x of 5. What's y?
Well, let me solve it. So, 3. So y equals 1.
Yeah. And there's our three answers. The cost of a slice of pizza is $5. The cost of a liter of soda is $1. And the cost of a salad is $3.
Okay.
And anytime you have three equations and three unknowns, it's almost always going to play out as that, okay? It's rare that you won't have all your variables on one side. In other words, all of these word problems are going to be the same. They're going to say this plus this costs this. Well, that leads you to an equation where all your variables are on one side and on the right side is just a number. So you end up with a system of equations almost always like this. It's very, very rare that they're going to tell you cost of soda is $1.
Yeah.
You know, in other words, you're always going to end up with three equations, usually three unknowns. In this particular model, the third equation actually only had two unknowns. Not that that made it particularly any easier. We still had to eliminate a variable.
Right.
And the variable that was the easiest eliminated was y. In other words, I don't have to do anything to the equations in order to eliminate y. I can merely add or subtract. If I wanted to eliminate z as my first variable, well, now I got to multiply equation number 1 by 3, right?
Right.
Okay, so I always eliminate the variable that I know I'm going to be able to eliminate easily. And since it's all plus y's, well, I can subtract 2 from 1 to eliminate y, and then I can subtract 3 from 1 to eliminate y. So I don't have to do any manipulation at all to these three equations in order to eliminate variables. Sometimes you will. In other words, if I had a problem like this, now this is only two equations and two unknowns, but notice that I cannot eliminate a variable right away.
Mm-hmm.
I have to do some multiplying. In other words, I got to multiply the bottom by, the easiest way to do this is to multiply the bottom by 3, both sides. Always remember you got to do both sides. And the top, and in this case I would multiply the top by -2, such that my result I'm going to be able to add. Well, what's this give me? It gives me -6x minus 4y equals -20. The bottom gives me 6x plus 9y equals 45. And now I can add the two equations and I get 5y equals 25. Y must be 5. And once I solve for y, I go back into either equation and then solve for x. No, it turns out x has to be 0. And
Yeah.
I just pulled these numbers off the top of my head. But once you do solve for y, you can solve for y by adding those two and then go back and solve for x, and it turns out that y is 5, x is 0 is the solution.
Okay.
Okay, not really any different. Three variables is just more complicated. And just always remember that with three variables you want to create equations 4 and 5 that become two equations with two variables only. In other words,
Okay.
the one mistake that people might make here is they maybe would eliminate y as their first step to get this equation. And then maybe they would try to eliminate x. Well, if I do that, then my second equation is going to have y and z in it. My first equation is going to have x and z in it, and I won't be able to solve it. Now I have two equations and three unknowns. So the key is to always eliminate the same variable in your equations 4 and 5.
Okay.
What else you got? But
Um,
remember that on word problem. If every student I've ever had hates word problem, bar none,
yeah.
okay? And I tell every single one of them the same thing. If you start the problem out by defining your variables, they become easy. And you always get your variables from the last sentence, almost always, not as if you run into some harder problems. You're in pre-calc, right? Or no, you're in Algebra 2?
Yeah.
Towards the end of Algebra 2, you might get some word problems where you can't just immediately go to the last sentence, but usually you can. You know,
Yeah.
there's adult tickets, there's children's tickets, they each cost something, and you bring in $100 in revenue and you sell 50 tickets. Well, the last sentence of that word question says, how many adult tickets did you sell and how many children's tickets did you sell? That becomes your variables. And in fact,
Okay.
when I see a word problem, I don't even read it. I immediately go to the last sentence. Truly.
All right. I'm trying to think. I don't know if, I mean, I guess we could identify the constraints, but we couldn't graph it.
Yes,
But
we can. You're talking about a linear programming problem?
yeah.
Okay, give it to me.
Okay, so it says the Coupler Model Company is planning to market a variety of electric racing car sets. Every set will contain at least 8 sections of curved track and 4 sections of straight track. No set will contain more than 36 sections in all or more than 20 sections of either type. If the company makes a profit of 40 cents on each straight section and 65 cents on each curved section, what combination of track sections will be the most profitable?
Give me your variables.
Um,
Look at the last sentence.
if the company makes a profit of 40 cents
Don't even
on
put
each,
that part yet. Just the very last part of the last sentence.
what combination of track sections will be the most profitable?
Okay, how about we let X equal the number of curved track sections
Okay,
and Y be the number of straight track sections,
okay,
right? Now, linear programming problems are without a doubt your hardest kind of word problem.
yeah,
But they all tend to play out the same way. We're going to have an objective function, which is what we want to maximize or minimize usually. And then we're going to have all these constraints. And what these constraints typically do is something like this. They define an area like that. And what you do is you take your profit function. Let's talk about the profit function for a minute.
okay.
What's the profit?
40 cents for straight and 65 cents for curved.
Is that right? Is that my profit?
Yes. Well, how'd you get 4? Oh,
40 cents
right.
times the number of straight sections.
Okay.
65 cents times the number of curved sections. That's how much you make. Okay? So that function is not shown in my graph ever. It's just the objective function.
Okay.
What you want to do is the graph is a graph of the constraints, and once you get an area, a region defined, you go in and find the vertexes of that figure, and you plug in the x and y coordinates into your profit function. Obviously, this bottom one here is 0, 0. If I plug that in, my profit's 0. So that's probably not my answer.
Right.
But over here, it's going to have a different set of coordinates. Now, let's talk about how to draw the graph here. That graph I just...
Well, you have to identify the constraints.
What's that?
It asks us to identify the constraints too.
Okay, so reread from the top again.
Okay. The Cooper Model Company is planning to market a variety of electric racing car sets. Every set will contain at least 8 sections of curved track and 4 sections of straight track.
Stop. So what's
Okay.
X?
X would be, or no, it would be X would be,
Less than or equal to 8, right?
yeah. And then Y would be less than or equal to 4.
Okay. What else?
No set will contain more than 36 sections in all, or more than 20 sections of either type.
Okay. So X plus Y is what?
X plus Y is greater than or equal to...
Less than or equal to. Every set will contain no more than how many?
36 sections in all.
And what's the very last part?
And more than 20 sections of either type.
They can contain no more than 20 of either type?
No, they contain more than 20.
I'm struggling with the fact that this constraint here said X is less than or equal to 8. And this constraint is less than or equal to 4.
Do you just want me to read you this sentence again?
Yeah, reread the problem again after the initial.
Okay. Every set will contain at least 8 sections of curved track and 4 sections.
At least 8. So every set has to be greater than or equal to 8, and Y has to be greater than or equal to 4. That's where I was doing it wrong. And then the last sentence again, the total X and Y has to be less than 36.
No, it says no set will, oh wait. Yeah, no set will contain more than 36 sections in all, or more than 20 sections of either type.
Or more than 20 of either type. So we also have X has to be less than or equal to 20, and Y has to be less than or equal to 20. So those are the 5 constraints that we have. Okay, now let's graph those.
All right.
Erase some stuff here. One difficulty is I don't quite have enough room to do all of this. All right. X has to be greater than or equal to 8.
Yes.
There's 8, and less than or equal to 20. So X is in that domain, correct?
Right.
Anywhere in that middle. Y has to be greater than or equal to 4, and less than or equal to 20. So now the common area is right there, right?
Okay.
But there's one more constraint. How do I graph X plus Y is less than or equal to 36?
Well, do you have to kind of change that equation?
Yeah, put it into Y equal mx plus b format. In other words, it really is y is less than or equal to minus x plus 36, right?
Right.
How do I graph that line, turn it into an equation to graph it instead of an inequality, and then we have to figure out which side of the line to shade.
Right.
Well, where do I start in graphing this last constraint?
Well, you'd start at 36, right?
Okay, there's a point right there, 36. What's the slope?
-1.
-1. So I'm going to go up, down 1, and to the right 1. There's a -1 slope, okay? Now, it also says, because it's an inequality, that y is less than that. So which side of that line do I shade? Below or above? And it's always below or above. It's never left or right.
Below.
Below, because y is less than. In other words, all you have to do is go to the y-axis, find a point below the line. That's the part we shade. Well, now that means our area of interest is right there. And there's only 3 vertexes. There's that vertex, there's that vertex, and there's that vertex. So the next step is to label each of those vertexes and then plug them in to our profit equation to see which produces the greatest profit.
Okay.
Okay, so let's do that. What is the coordinate on that point? There's our area. Let's call that coordinate 1, coordinate 2, and coordinate 3, just for talking purposes. What's the x and y coordinate on coordinate 1?
Would it be 820?
8,4? Is that what you said?
No, oh wait, for 1. 8,4. Okay, yeah.
Okay. What are the coordinates on point 2?
820.
And coordinate 3?
Would it be, that one, that's not 20, is it?
Well, what is the y coordinate?
4.
Okay, now go back and plug in 4 into this. What do you get for x?
Oh wait. Y is 4, right?
Yeah.
Um,
In other words, we can see that y has to be 4. It's crossing that line at 4. I'm not sure what x is because I just kind of drew this without being super accurate. So I don't know what x is. But I can figure it out by going to the inequality that I have circled and substituting 4 for y. X has to be 32.
Right.
And y is 4. Now, that actually makes my picture wrong. If x is 32, let me go back and redraw my picture because it does matter. In other words, I know I'm starting at 36 and I'm crossing everything more like this, right? So I actually have 4 vertices. There's my point 3, and I have that. We'll call this fourth vertice of 4. In other words, the figure I actually created was not a triangle, but a quadrilateral.
Yeah.
Well, the quadrilateral has 4 vertices, and I ignored one of them, but this one is correct, right? In other words, as long as what I have circled here is the equation of that line, well, I can see that my x-coordinate is 4. Oh, excuse me, my x-coordinate is 20. So actually, on my coordinate 3, let's go back here. I'm probably confusing the heck out of you, but that's because I drew it wrong. For point 3, my x-coordinate is 20.
Okay.
Right?
Right.
In other words, it goes straight up from 20. So I know the x-coordinate is 20, which means the y-coordinate has to be 16. That was a 36 there. All right, and then I have one more point. Point 4, which is easy. X-coordinate is 20, y-coordinate is 4. Are you with me now?
Yes.
Okay. And this is very typically what you're looking at on these linear programming problems. They don't generally make it so easy that it's just a triangle. Usually it's a quadrilateral or even a 5-sided figure, depending on how many constraints you have. Okay.
Okay.
And in fact, this is a 5-sided figure. I actually have another vertex right there. I have one here, I have one there, I have one there, I have one there, and I have one there. I have a total of 5 vertexes.
Okay.
And how do I find that vertex right there?
Well, we know it's on 20.
So what's x there?
It would be, hold on.
If y is 20, x plus y has to be less than or equal to 36, so x would have to be 16.
Okay.
Okay, so there's my 5 vertexes. Now what I'm going to do is plug in each of these x and y's into my profit function to figure out which one gives me the maximum. Well, I can see right away that 1 isn't going to do it, right?
Right.
I mean, 2 is going to make more money than 1 for sure. So we don't need to worry about 1. Well, what does 2 give us? What's 0.4 times y? That's 8, because y is 20.
Right.
Plus 0.65 times 8. What's 8 times 65? That's $5.20. So we make $13.20 if we use coordinates 2.
Okay.
And also, I can tell that 2 is not going to give us as much as 5, because y is equal to 20 in both cases. So I wouldn't even have tried 2 if I had noticed that. I'm going to try all of these 3 here that I know one of the solution has to come from one of these 3 points, either point 3, 4, or 5.
Okay.
Well, x gives us more profit than y does, right?
Right.
So the bigger x, that is going to be better than that, for sure. In other words, 3 is going to be better than 5, merely because I'm multiplying the 20 times 0.65. But technically, I wouldn't do any of that sophisticated analysis. Basically, the methodology is you go in and you plug in each coordinate for x and y, and whatever produces the most p, that's the that's what you produce.
Okay.
Okay? And all of these constraints can be very legitimate. In other words, you maybe have only so much raw material to produce these tracks, or limited means of producing curved tracks, or maybe
Yeah.
started with 36 pieces, and that's what maybe your machinery. In other words, these constraints come from real life concerns, but it's not at all obvious as to which set of X, Y is going to produce the greatest profit. But I can tell you right now, it's this one right here, number 3.
Yeah.
And it usually is. It's on one of these corners there. It almost never is the number 1, because that's low X and low Y.
Right.
And it's rarely on these corners here either. It's usually that one or that one. Why is this not writing? Wow. Huh. Hold on. I may have to close this out and reopen it. No, there. Now it's writing. Okay. The advantage of linear programming problems are very similar to the advantages of 3 variables and 3 solutions or 3 equations. They're not going to be more than 1 on a test because they take too long to do.
Okay.
Each one of these is, and this was a 15-minute problem. The last one was a 15-minute problem. So you're not going to get a lot of these. In fact, I'd be amazed if you had a test that had a linear programming problem and a 3-variable, 3-equation problem.
Yeah.
Just because they're so hard.
Mm-hmm.
But the thing to pay most attention to in the linear programming is that your objective function shows up nowhere on that graph.
Yeah.
The graph is made up of all of the constraints only. And the combination of all of those constraints will leave you with a certain area of the graph. And whatever that area is, figure out the vertexes and plug in each vertex into the objective function. And that's, once you approach those like that, they're not hard. It takes a little getting used to figuring out how to graph that, an inequality, but not really. I mean, graphing inequalities that are linear, just put it into y equal mx plus b format, graph it like a straight line, and then shade the proper area.
Okay.
Okay? All right, Anna. Wow. Those might have been more like 20 or 30-minute problems, huh? They sure consumed the hour. I do have a 5 o'clock that I have to run for, so I will talk to you on Wednesday.
Okay, awesome. Thank you.
Okay, bye-bye.
Bye.